All right. So today we literally have one slide left on our lecture 4.1, which is basically pointing out what are the good programming practices that you can employ, and it'll help you find what we call avoidable errors in computing. Those are things like typos. Now, it might look trivial to you, typos, but we are very human, and humans do a lot of typos, okay? And a lot of mistakes that they don't necessarily notice. And when those mistakes actually have an immediate or create an immediate problem in programming, then it's easy. You know that they're there, and you're going to find them and address them. Finding them might take a moment, so that's simply there for everyone. So you have to kind of build up a little bit of resilience in just constantly looking for errors and constantly fixing them. This is something that you do even if you have like years and years of experience in programming. Okay? That's simply there. If you were in the lab, you would constantly look for leaks if you were in anything related to fluids or so. No matter what, be on the lookout for mistakes and be ready to spend some time looking for them. So those are avoidable errors, but they're necessarily there. So you have to basically be on the lookout specifically, because sometimes you will not be able to spot the mistake easily, or it's somewhere in the part of the code that you haven't tested. And as you build the code, like when you write the first program, you have a specific problem in mind, and it might be working perfectly for the problem that you designed it for. However, with the next data set, you might actually discover the parts of the code that they're not working as expected. So always be on lookout for that. With new data sets, new problems that you're trying to solve with the same code, you will find new errors and new things. It's not necessarily even errors. It's basically you have to expand the code to address certain issues there that you simply did not detect before. So that's why it's important to, at least preliminary, when you're solving on an important problem, find the problem that you can solve by hand so you can test your code against that it's working well in that solution and giving the solution you expect. But that doesn't mean that you have weeded out all of the errors just because you tested it on a number of examples. Okay? So be ready that as you kind of test things, you will find more errors. Now, just a couple of more points. I think I pretty much stopped here. So one thing that helps is basically organizing your code, as we said. So this is a good example where you want to give yourself a hint what is the code supposed to do, and also provide some sort of basic how are you supposed to use the code, what is the input supposed to be, what is the output supposed to be, and where is the further notes about the method you implemented, because that too will help you find errors in future. Also, when you are writing a program, you kind of want to organize it such that you have this description of what the code does. You process all of the input all at once, so any errors that show up, they show up immediately and not in the after 3 hours of computing. Okay, and then you perform a computational task and prepare output to go out. Now, you might not notice the difference in mixing these two up right now, because everything that we do executes literally in milliseconds. But there are, in my own research, sometimes simulations last for 3 to 4 weeks. Now, you don't want in week one, after week one of computing, you don't want to say, oh, computer tells you, I didn't know how to read this file. You want to read in all of the files at the beginning that you can, okay? And basically then proceed without errors, hopefully, onto the computational task and then keep computing. So it is important to do things in order and do all of the things without delaying that you can at the very beginning. So any errors, they show up immediately. Okay. Now, a couple of tools that can help. Control C stops a running program. Type commands or even debug type. So if you type the file name, you will actually list contents of any M file if you just give the file name. Basically command. You can actually type only a portion of the file. So if your program is reporting an error on line 20, you can actually go and type or print your lines from 19 to 29 to see where the problem might be. You can also type in pause in the middle of your program. That will pause the program until it's ready to continue. And you can actually insert breakpoints and step through the program. I'm actually going to just quickly show that. So MATLAB is interactive. So when you insert a little breakpoint, it can stop. The moment the program hits that line, it will stop, and then you can interact with the program. Okay. So let's do anything really here. I'll open one of these problems. So I'm gonna insert a breakpoint right here. Okay. And I'm gonna run it now. This is a script, so I can just run. And little k here means that I'm in debugging mode. So it literally stopped first time encountered that line. And now I can say, I don't know, print x. Okay. And then I can say db continue. And it's gonna stop next time on that line. I can now print x. Oh, now it's 0.5. Okay. And db continue. And now it's next time. It's going through the loop. Okay. So it's basically stopping every time it hits that place, which if the program is reporting a problem in that spot, then you can actually interact and figure out what the problem is. Okay. So, and it's as quick as simply placing a little point here. And you turn it off by clicking on it again. So I find this one of the quickest ways. Another simple way, without actually interacting with the problem, is to print the contents in the line that is reporting a problem. For instance, so here we don't have an example of a problem, but let's say that my program did. You can basically report, oh, there's an issue on line 7. You simply print things out so you can see what are the values and what the problem might be. Okay? Or again, you click on this to make it an active, and you will have to save the contents of the file in order to for this to become inactive. So right now it's inactive because I need to save. Okay. Oh, okay. You cannot save the file. Okay. So now it's saved and it stopped the debugging, so I have to go do it again. So a little red dot shows that it's an active breakpoint. So this, I think, is the most useful command. So in what is expected of you is that basically you start working on those programming practices, especially in homework. Okay, so organize your code cleanly, do a well-structured program, use the debugging tools to fix them. Now I will not test you with actively writing a program on computer. Okay? During the tests, but during the tests you actually have to write them down. So that will enable you to write them down cleanly during the test. Of course, I'm going to be a little more lenient in terms of, especially, I'm not going to expect you to do a great commenting on the what you're doing in the code that you write by hand during the test. So that part is fine. But the more comments you do provide, I know what your thinking was, so I can actually give you extra points for that. Okay. So that ends our lecture on 4.1. And now we're going to start with errors that essentially we cannot avoid. So now we're going through the second part of the lecture 4 on unavoidable errors in computing. And once we finish that, we will actually start working on numerical methods. So all of this is sort of introduction to programming practice, more than solving specific problems with numerical methods. And that basically starts from lecture 5 and on. So when we call something a bug, it's typically a problem that we can avoid and that has been created by our being not very careful. And this fixing the error is called debugging. Okay. Now, there are certain errors that are there in programming that we simply cannot fix. Where do they come from? First one is truncation error. So you know in math that a lot of sums go to infinity. Okay, so they keep going on and on and on and on. Well, in practice in computers, if you're going to compute this sum, you cannot just keep going on and on and on and on. And arguably at some point, the difference between stopping at 10,000 and keep going is not something we will be able to detect anyway. Okay, so we actually have to stop and make these finite sums, and any mathematical formulas, they actually have to be finite and not infinite. And in that, we're going to create an error that is called truncation error. Okay? So any approximation to a continuous sum or function with a finite number of values is truncation error. Second one is the round-off error. So we know that numbers, for instance, like pi, they have their digits keep going, and we actually don't know the end of it. Well, we can't keep storing those values, nor there is practically a need to. So at some point, all of the numbers have to be chopped off. Okay, and that is what we call a round-off error. There's simply finite space that we're fitting real numbers in. And some numbers can be represented exactly, but most of the numbers have some round-off error built in. Second thing is that we're going to see that, like in computer memory, computers are stored in a very specific way. We also often have to tell computer which type of number are we storing, because there are different ways to store different numbers, meaning, for instance, integers versus real numbers. Okay? And in that process, there are things that will be chopped off. And then there will be errors related to any kind of computation with those numbers. For instance, if this number, there are two issues. This number could have, for instance, way too many zeros here, so that it in itself cannot be stored correctly. So it's going to be treated as a zero. Okay? That's the problem number one. Second problem is that, and we will see, due to a specific way that real numbers are stored, this number might be stored correctly, and this number in itself might be stored correctly. However, these two numbers are so far apart that when I attempt to store when I add them up and attempt to store that number might not be stored correctly. And it's going to be rounded off back to 1,000 in this case. Okay? So it's going to go at the expense of the smaller number in this case. So basically, it's this procedure of adding two numbers that are very far apart that is going to create a round of error in itself. So first problem would be that number in itself might not get stored properly, and second part is that I'm adding two objects that are kind of too far apart, and one of them will get rounded off, and the result is not precise. Okay? So those are the problems. So first we have to agree how do we measure errors. Okay? And I have first absolute error, that is simply the absolute value minus true value, the value that is supposed to be stored, and the approximation. Or in this case, it could be actually simply the numerical method that has certain errors. And basically, if I have true length of a bridge as 100 centimeters and I measure 99 centimeters, that's a very short bridge. Then I have 1 centimeter. It's more of a bridge over a small brook rather than a river. Okay. So then my absolute error here is 1 centimeter. River itself might be much longer. It's not a very long river either, or wide river. And this could still be 1 centimeter. Well, 1 centimeter compared to 1,000 centimeter and 1 centimeter compared to 100 centimeter are not the same thing. Right? So relatively, I'm not making the same error, in which case we actually want to, relative error, in my opinion, is way more useful because it kind of normalizes how important is the error relative to the number we're trying to measure. So again, relative error in this case is basically 1 centimeter divided by 100, which is 1%, or 0.1%. Okay? So 0.1%, we can say it's not all that important. And for the most engineering purposes, it's okay to have an error. Okay? If I'm trying to drive to San Antonio, I kind of need to know roughly how much gas I need to put in the car. I don't need precise number, nor that this knowledge of a very precise number help me when I get to the pump. Okay? So as long as I'm in plus minus range that I can safely get there and come back, that would be, that's basically enough. So for a lot of engineering purposes, we don't have to be super precise. But we do need to know what is the type of an error that we make. The same is not true, of course, if you're trying to cut something with a laser. You have to be very precise. Okay? So it depends on the application. Okay. So let's look at the truncation error, and that is approximating continuous expressions in math with their finite version. So let's say that we have a series representation of exponential function. We know that e to the x is 1 plus x squared over 2 factorial plus x to the cube over 3 factorial and so forth. Okay? At some point, when I'm computing this, I will have to stop, okay? And that will cause a truncation error. So another common example is the derivative. Okay? We know that my derivative, by definition, is basically I go from its difference in the values at two different points of a function divided by the distance between those 2 points. And I tend to kind of make those differences smaller and smaller and smaller and find the limit. So that is my mathematical definition, is that this is the limit of this as delta x goes to 0, correct? In reality, we will really have a discretized version of a function. So what I will store is an array of numbers that are evaluated at equal distances. So that's called discretizing a domain. And my derivative of a function will simply take two closest points that I have values for in that domain, look at their difference and divide by the difference between the points, and that's going to be the definition of my derivative for this numerically defined function. Okay? So this can work with the function in itself that is defined like this, and it can simply work with data. So if you're taking a well log, petroleum engineering, you can simply have data versus depth. Okay? And you don't have, you have data every half foot or 1 foot, and not better than that. Okay, so you have values at discrete points, you can still define a derivative in this particular way, even though you don't have an actual expression for your function as a function of depth. So it's not an exponential of anything. Okay? So in that sense, this works both with data and with actual functions that have mathematical expressions. But there is an error, of course, involved in this approximation. And there are different approximations you can make for derivatives. We're going to go into that a little more later. Right. So formally, I have Taylor series. They're used to derive and analyze numerical methods a whole lot. And if there's one theorem that is important from your calculus, is it calculus 1 class? Or whatever is the math 420 something that you took here at this university. So basically, at every university and in all formal education, there's some variant of calculus 1 in which you go over Taylor series, and that's one of the most important theorems for analysis in practical engineering situations, because it tells me what the size of the error is, so I know what to expect when I'm programming things. So it says that a value of a function at a point x is the value of that same function at some nearby point that we're describing as x0 plus difference between the two times the derivative of the function evaluated at x0. And then you can keep going, actually, there's these terms. So basically you also have the second order derivative, and then there would be a third order derivative, and so forth. Now these parts here, especially if as I'm getting closer and closer to x0, this number is going to be a small number squared versus that same small number. So these parts will be smaller and smaller and smaller as I get closer to x0. Okay? So at some point I can really neglect these points because I'll be accurate enough. Okay? So essentially we can only take the first certain number of terms, and based on how many terms we take, that determines accuracy of my method. For the most practical purposes, we are stopping at 1 or 2 terms here in terms of derivatives, and we're chopping off the rest. And that tends to work just fine. Okay? But we need to know the size of the error as well. And then my error, depending on how many I chop off, I know that actual error is a value of this n plus 1th order derivative of f somewhere in between this x and x0, okay, times this number. So if this derivative is well defined, then I can actually figure out what its size is on that interval. I can actually place a pretty good sort of like I can feel out what this error is going to be in size, and that's very useful in analyzing numerical methods. All right. And then we will also often, simply to stop the time when I'm working in a numerical method, I'm going to actually test what my size of the error is, and I'm just going to simply stop at some point when I think it's enough. And I think we had an example in your homework of finding the square root of 2. Is that correct? So you throw in an epsilon in there, say, okay, I'm fine as long as I find this to the error of 0.001, okay? And where do you stop depends on what the application is. In the previously mentioned driving to San Antonio, plus minus a gallon of gas is just fine, okay? And that error that you make, as long as I guess you're in a plus part. But in certain other applications, you might want to be much more precise, but that's something that is up to you. So you will have some current guess, and you will have an actual solution, and you will stop when you're close to it. If you don't know the actual solution, then you will simply look at the previous, as you're iterating through, you're going to look at the previous value in the previous step and the step currently, and as long as this is getting close, you're saying, okay, I'm converging to a number or a value, and I'm getting close enough, so I'm going to stop when I'm less than this. Well, I named it delta, not epsilon, but epsilon and delta are common numbers that denote like stopping criteria. So that's basically about the truncating error. Let's actually maybe do an example. So there's an exercise at the end of this. Okay. So let's do this number 1. Write down the formula for f of x is 1 over x plus 1. Close to what we're going to take is x0 is equal to 1. So first write down this formula evaluated specifically for x0 and this particular choice of f and x0. So then once you have this formula, you can evaluate both f of 3 and f of 2 using 1, 2, or 3 terms. Okay. And calculate relative and absolute errors. So I think it would be very good to actually have a little table. And you can do that by hand or you can do it on the computer. I think it would be useful to do it by hand, but you help yourself in computing things. And you keep doing it, and I'm going to kind of do it using MATLAB myself. Questions? can we figure out if the number of terms is only one, so I only have this? What does Taylor series formula tell me that f of 2 is? Same as f of 1, right? Yes? No? The formula says that near f x0 is equal to 1. So x0 is 1, so my f of x is f of x0, which is literally 1 over 1 plus 1, right? Plus x minus 1 times what is derivative of 1 over x plus 1? Minus 1 over x plus 1 squared, right? And plus x minus 1 squared over 2 factorial is 1 times 2, so that's 2, times what is the derivative of this? Yes? And keep going. We don't need to keep going more than 3 terms. So this now continues with the fourth order derivative. Great. So my actual formula says that f of x is equal to 1 over 2 plus x minus 1 times minus 1 over, this is actually evaluated at x0, so this is 1 and this is 1. So minus 1 over 4. So I can just write that as a minus 1. And this is 1. This is 1 over 8. So plus x minus 1 squared divided by 8. So this is what my f of x is approximated as. These 3 terms, 1, 2, or 3, depending how many I want to take, near x0 is equal to 1. Now let's see what is the error we do for that type of thing. So let's say that I want to say 1 term. So that is this one. Then my f of 2 is simply that 1 term, which is 1 over 2. So that is my value, approximate value. What is my true value of function f at 2? 1 over 2 plus 1, yes? That's my actual function is 1 over x plus 1. So that is 1 over 3. So what is the error I'm making? If I take this approximation, which is very crude, it's just a constant, I'm going to make an absolute value of 1 over 2 minus 1 over 3 is an error. Okay. And relative value, so error, absolute error, will be 1 over 2 minus 1 over 3 absolute. And relative error will be that same thing, just divided by the true value, which is 1 over 3. Absolute. Now I can take 2 terms, so then my approximate value will hopefully get a little better. and again evaluate these. In 3 terms, and evaluate. And I could repeat for f of 3. So again, approximation to the actual function 1 over 1 plus x is given by Taylor's theorem. Okay? And that theorem has as many terms as you'd like. But in reality, you're going to evaluate only a number of those. So we're just testing how accurate the formula is if we evaluate it with 1 term, with 2 terms, 3 terms. We could actually keep going. So this is what my actual approximation of this function looks like. And then I'm looking at the errors. Now, I don't like doing things by hand. This is why I'm programming business. So I'm actually going to show you how I quickly programmed it on the computer. So I gave myself, so again, just a reminder, f of x is 1 over x plus 1. This is the derivative, and this is the second order derivative of that. And my x0 is 1, and I'm going to have a little script that asks user for x value, which I'm going to put as 2 and 3. And my true value is 1 over x plus 1. Now, depending on the number of terms, I'm going to actually evaluate So I actually created a function, Taylor formula, that takes x0, x and number of terms. So it starts with 1 over x0 plus 1, which is 1/2 in this case. And then if I have number of terms that is larger than 1, I'm going to add this next term, okay? And if the number of terms is larger than 2, then I'm going to add the second term. And if it's larger than 3, I'm going to say, sorry, I do only up to 3 terms in this particular case. And I think I made a small mistake. I was supposed to divide by 2 here as well. Okay, so this is square. And also 0.5 times. Okay, but since this, so I can, sorry, I'm doing things on the fly here. So I don't have to multiply, I'm just going to divide. Okay. So now I can run this. Give me x, let's say 2. Oh, I didn't print anything. So for now, I just calculated absolute value. We're going to finish this next time, but let me run. If I do 2. So basically for the number of terms 1, my value is 0.5, and my absolute error is basically difference between 1/2 and 1/3. If I have 2 terms, value is 0.25, and my absolute value is smaller. And if I have 3 terms, this is the value, and then I keep getting smaller. So as I keep adding terms, I'm going to get more and more accurate. Okay? And we're going to wrap this up on Wednesday.